There are other options, however. This is a picture of a receiving dock or loading station for offloading station for one of the wastewater treatment facilities. And so what they'll do is, if you've been out on the road, you probably see the tanker trucks out there that say residual waste on them. Chances are nowadays they're hauling flowback water to a recycling plant or a treatment facility. And so they'll bring it in and they'll offload that water, and then the facility will run it through their treatment scheme. So some of the options out there would be direct reuse of the flowback water. In essence, just blend it with fresh water on site. So you're getting at the wellhead, again, 8 to 10% of that water that you've injected down in the well returns at the surface. And so if you capture that water, which you have to do, and you blend that water with fresh water, you might be able to dilute any concentrations of contaminants of concern in your flowback water and directly reuse that water. That might work real well. There's minimal cost associated with that. The potential downside is if those cation concentrations remain high enough in that blended water, again, you might have potential for downhole scaling. There's a lot of companies out there that are now providing on-site treatment services. They might use a chemical type of treatment like we just discussed. They might use a filtration type technology out there. But what they can do is, again, fairly effectively remove the cations out of the water, those scaling agents, and recycle that water. There's going to be obviously some cost associated with treating that water out there in the field. One of the major advantages is that you reduce your transportation costs because you're not hauling water to a treatment facility. And the transportation costs are fairly significant. To have a truck hauling water costs on the order of $80 to $100 an hour. So you start doing the math, and that can add up pretty quickly. Not to mention the health and safety considerations with all the truck traffic and the beating up of the roads, because there are a lot of roads that are getting pretty beat up by all the heavy loads of trucks going up and down them. So by doing on-site treatment, again, you would minimize the risk of downhole scaling. There is, however, a price tag associated with that. There are several off-site treatment facilities now where you can take your flowback water to a treatment facility. They'll do basically chemical type treatment, and then you can take that recycled water. They'll basically give you your water back, your flowback water. You haul that back out to your well site operation, and probably blend it with fresh water to make up the amount of water you'll need to hydraulically fracture your well, and away you go. Again, you reduce the risk of downhole scaling, but you are going to have relatively high transportation costs because you're hauling it not only to the treatment plant, but back from the treatment plant out to the well site. So that gets expensive. The other option is just total disposal. Take it to a treatment facility that's permitted to take the flowback water and let them treat it, and you don't recycle it, and you just start with fresh water every time. Again, you'd have high transportation and disposal costs. So those are basically the four options out there being utilized for Marcellus development in Pennsylvania. There are some, beyond just the chemical treatment, there are other treatment options for high TDS waters. There's electrodialysis. However, the maximum influent TDS load's about 40,000 parts per million. And so if you've got water that on average is going to be on the order of maybe 75,000 parts per million TDS, electrodialysis isn't really going to work too well for you. Reverse osmosis, basically the same boat. It might treat some of the, that early water that comes out of the, during the flowback event that hasn't been in contact with the formation and doesn't have as high of a TDS concentration, but the bulk of the water is not going to be able to be handled by reverse osmosis. Evaporative technologies, I should say, are being utilized on some level. There is at least one facility in Williamsport that's now using what they call mechanical vapor recompression. which basically brings the water up to near boiling point so that you separate the salts from the water through, in essence, boiling it. And the process is more efficient than just straight boiling, because what it does is recaptures the heat and puts it back into the evaporative process. And so it's much more efficient than just straight boiling of the water. But again, the upper end of the influent load on that's about 100,000 parts per million TDS. There's also membrane distillation, and crystallizers have also been discussed as potential treatment technologies out there. The problem is most of these treatment technologies are relatively energy intensive and therefore relatively expensive, and so they're not very cost effective. So again, the industry is looking for cost effective treatment technologies, and it's kind of hard to come by. The mechanical vapor recompression technology seems to be the most popular choice for those selecting an evaporative technology. And as I said, there's at least one facility in operation in Williamsport handling on the order of a little over 100,000 gallons per day. And actually that treated water is then being actually discharged to the Williamsport Sanitary Authority system until they can actually recycle it. For some permitting reason, they can't recycle that water right now, but they're working toward that. So this just gives you a typical run-through of a treatment scheme. So you would have some sort of brine water storage tank. You bring the truckload of flowback water in, it's stored, it's run through a sedimentation tank, and then you would add a coagulant and basically get the metals to drop out of the water, as we discussed. So you use something like a sodium hydroxide to get the metals to drop out, and then you'd run it through a clarifier. And what the clarifier does is that essentially gets the solids to drop out. And then those solids would be run through a filter press to dewater them. And then you end up with a fair amount of sludge at the end of the day that would need to be hauled off to a treatment facility. What this sludge is going to hold is most of the things like barium and strontium that would be otherwise found in the flowback water. And so the water that goes through the clarifier, that clear water, has been treated for the metals, the cations, and so the barium and strontium levels have been reduced greatly at that point. Again, recently in the press you saw that, at least the article stated that barium and strontium tainted waters are being discharged into our streams and rivers, but didn't really touch on the fact that on the order of 95% or more of the barium and strontium is actually removed during the treatment process. And so that was a little misleading as far as the way that read. So once that water is been treated, you can recycle that water for hydraulic fracturing, or if you may be able to dispose of that. Now, there's a bit of a wrinkle in there in that there are on the order of 9 facilities that predated the Marcellus that are able to discharge high TDS waters to our surface streams. They've been doing that for many years, associated with the conventional oil and gas industry here in Pennsylvania. However, as their permits are up for renewal, that high TDS discharge will not be grandfathered in the future. And so, in essence, the high TDS discharges to our surface waters will be phased out over time, probably over the next 5 years or so. I spoke to one of my colleagues at one of the water recycling plants in Williamsport, and he was kind enough to share some of their information with me. I thought it'd be important to bring some real-world data in here. And so the Terra Aqua Resource Management facility is in Williamsport. And they use the chemical precipitation type of treatment technology. Again, that's fairly conventional treatment technology to get the metals to drop out of the water, to get those scaling agents out of there. And so they average about 150,000 gallons per day at their facility, and they can handle up to about 400,000 gallons per day if need be. Oops, I missed a zero there, sorry. And so they generate out of that sludge that drops out of the process. They get about 8 to 12 tons per day of that sludge, which is then taken to a landfill that's permitted to take that type of waste stream. But before they take it there, they have to characterize that waste stream to ensure that it isn't classified as not classified as hazardous, I should say, so that a typical landfill would, in essence, be able to take it. So they go through what's called the T-clip testing, and so that's basically a toxicity characteristic leaching procedure. So what they do is they take the sludge, and they'll try to, in essence, try to create leachate out of it. And it's that leachate that they then test to see what the concentrations of the various constituents are. And if those concentrations stay below a certain threshold, the landfill can take it. If they were to exceed that threshold, it would have to be classified as probably hazardous and need to be taken to a hazardous waste landfill. Based on their data, for the last, they've been in operation since April of last year, so they've got about 10 or so months of data. They found that through and through all of their testing, they've never had to classify their sludges as hazardous material, so it meets the non-hazardous requirements. One of the other things I'd asked about is the radiological monitoring. There's a lot of concern about the potential for naturally occurring radioactive material, known as NORM, in the water and then therefore in the sludge. And based on, again, he said about 8,000 data points, the flowback water that comes in, they screen it, and their maximum flowback readings about 12 microrems per hour, and they're permitted at 175 microrems per hour. So they're well below that radiological limit. Now, during the treatment process, as the cations drop out, the norm will tend to drop out along with it. And so, in theory, then the naturally occurring radioactive levels would be higher in the sludge. And so that is the case, but again, they're still below that limit of 175. They've got about 20 to 80 microrems per hour. So again, they're well below the limit to be able to dispose of this sludge at a landfill. What they are finding is that the primary radionuclide is radium-226 based on their testing. So that's the typical treatment scheme we're seeing out there. Now, even if you did use an evaporative technology, you would still need to do some sort of treatment scheme like this, because you'd still need to get those metals out of your water. Otherwise, you're going to pretty much scale your heating elements in your evaporative technology pretty quickly. And so this is still a necessary type of treatment technology for the industry. Now, when this flowback water comes into a facility that's going to discharge to a surface water, the natural gas company is required to test for a variety of constituents. There's, I believe, 51 constituents on here that are all very specific to Marcellus shale produced waters. And so what this allows is the operator to characterize their flowback water stream, provide this data to the wastewater treatment facility, and then they can see if they meet the limits that they have at their facility. You're not allowed to discharge your water to a wastewater treatment facility unless you provide the proper characterization by analysis of all of these parameters.